I'm gonna just continue about stereolithography and the basic parameters and process and part parameters, which is gonna differ the part quality in based of both the part accuracy as in dimensional form factors and surface roughness, at the same time part strength as in tensile fractional strength and all that. So just gonna start with on video. So this is an actual company which does that. You can just get a code for whatever part you want to make. Just tell them they make their. I mean, tell them what you want to make. They get their designs and do all that. So as usual, it just starts off with making the CAD diagram and then slicing it up to an STL file. I mean, different layer thickness based on your um, printer properties. And it just shows how the laser works as in cures along the vat which contains the resin, and you have annotations which actually tells you what it's done as well. So they don't show you much about each layer, so it's pretty much now it's done. They're just bringing it up. They're gonna remove the supports, and then as always they have to do post curing, so they put it up into an oven. Sorry. Oh, okay. So the thing is, there's this since the Z stage is independent of the VAT. Okay. So the thing is, they have different VATs having different material. So whenever they want to, so if you have to use a different material for the different layer, it kind of shifts the VAT so that you can trace that there, and then the layer is separated using the. It's pretty much a new thing they brought about now, like probably a 2 years or 3 years back, I guess. Yeah. They haven't actually mentioned anything about what machine they're using. Yeah. So I've changed a few things as to what comes over here. So build time, as in, even though build time is one of the important characteristics which determine is it's more about dependent variable based on layer thickness and all that things. So we the two things which I added instead of build time was post curing as a separate factor, and also overcure. Overcure is what I mean by overcure is the depth to which the excess depth to which the laser actually cures the polymer, apart from the layer thickness after it cures the layer, like how much it cures after the thing. So that one, and then part orientation, and then as usual just layer thickness. Most of the papers I found were pretty much Taguchi parameter analysis. So they just randomly choose. You can't say random, but they choose their parameters or factors. So this one is they try to optimize the process parameters to enhance their tensile strength of the part which they manufacture. They do Taguchi parameter analysis. They choose three factors and then they choose three levels each. So the levels which they've chosen, they say is based on machine and material. They're using the SL 250 by 50 machine, which is one of 3D Concepts earlier machines. Sorry, 3D Systems earlier machines. And the process parameters which are tested are layer thickness, orientation, and post curing time. So post curing time, they say, is even though we're gonna do, it's not mostly a process parameter. Like once the part is built, post curing is one of the most important things which they have to do. So they're saying it has to be included in it. So these are the levels of each things which they've chosen. So and for orientation, they choose four different things, which is completely random. I have no clue what it is because they haven't explained anything about what HX or VX or anything is. So the post curing time is dependent upon layer thickness, and they've kind of considered interaction between factors as well, which usually they don't do when they're doing parameter analysis using Taguchi's method. And the interaction is something which even in this paper and a lot of other papers, they're not actually able to explain how the interaction, I mean, what kind of interaction is there between the factors and how it affects. Even though the interaction does create a significant effect in the process as per their analysis, they're not actually able to understand or give us a explanation as to why it happens. So this is like the experimental plan. They just take up their problem is part strength, and they look up at tensile strength, but they say the system which they're doing can be extended for fractional strength and all other mechanical properties as well. So it's just the same thing, orthogonal arrays for three factors with three levels. So this was their thing, and the SNN, they try to maximize the signal to noise ratio, so in order to obtain the maximum tensile strength possible, and they kind of try to map which property, I mean which factor levels which they chose has the maximum, which can provide you with the maximum tensile strength. So for layer thickness, it was around 0.1 millimeter, and then for post curing time, it was about 60 minutes, and the orientation, the VX orientation, which pretty much kind of means vertical, something related to X. So yeah, and this is kind of the percentage distribution of how the factors, which factors influence the tensile strength of the part. So it was seen that part orientation was the most significant factor which affected part strength, which is followed by part curing time. They kind of see that layer thickness does not provide much influence, but the layer thickness interaction between layer thickness and post curing does create a really huge influence on the process. This was kind of a empirical regression model which they created. So it was okay. They do pretty much like 30 to 40 experimental runs to see how their regression model, the tensile strength obtained from their regression model and the actual tensile strength tested varies, and they kind of have just around like 6% deviation from the average value which they obtained from experiment and the regression model. The next one is this one is more about dimensional accuracy, form factor, form errors, and surface roughness. So in this one, they try to do, they have a part which has 20 different dimensional geometric and surface roughness values. Their part is kind of complicated part which gives you like a lot of analysis to do. They're using Taguchi's method as usual. It's the same thing. In this one though, they're using 5 controllable factors with 3 levels each: layer thickness, hatch spacing, and this is where they bring about overcure, blade gap, and the position of the build plane. So that is their part design. Kind of has a lot of cavities, some moles here and there, some cut edges and all that. It was seen that most of the times it was just layer thickness and blade gap which provided most of the significant effects, but it kind of differed based on what kind of accuracy we're looking at. So if it is dimensional, horizontal XY dimensional accuracy, blade gap was the one which played the maximum effect on accuracy, but on geometric forms, layer thickness actually played a very important role, and most of the things other than that, it was just layer thickness, like the vertical dimensions and then surface roughness. There wasn't actually process models. This is again the same regressional empirical model which the old paper had suggested. I just put this up because at least they have some kind of relation which shows and thing. And LTE is layer thickness, post curing time, PC is post curing time, and O is orientation. I do not exactly know how they account for orientation as a quantifiable factor here. So that's up to us to just assume. I mean that's the. So these are my references.